Assalamu alaikum to everybody. In the previous class, we were discussing about Dalton's law of partial pressure. Okay, we have finished that one, and there was a small homework known as uses of Dalton's law of partial pressure. Okay, can anybody tell me at least one use of Dalton's law of partial pressure? Open up your notes and what you have written in homework yesterday evening at home. Just refer that one and tell me what are the uses of Dalton's law of partial pressure. JL41, roll number 17, Saifullah. Can you tell me what are the uses of Dalton's law of partial pressure? Anybody out of 37 students? Anybody? It used to find out the pressure of individual gas in a mixture. Abdullah Sohail Ahmad. Excellent. Very good. Nice. Anybody else? Abdullah Sohail Ahmad is saying that Dalton's law is used to find out the pressure of individual gas in a mixture of gases. Sohail, roll number 17, JL41. Can you tell me? I know that you have not done homework. Can you tell me this now name, the meaning? Sohail is saying it is used to find the pressure of individual gases in mixture of gases. What is the meaning of that individual gases in mixture? Pressure of individual gas in mixture. Saifullah, can you please tell me? I know that you have not done homework. Uh, can you please at least tell me what is the name of pressure of individual gas in mixture of gases? Saifullah is saying that Sir Dalton's law is applicable to find out the pressure of individual gases in mixture of gases. Excellent. What do you mean by the word pressure of individual gas in a mixture of gases? चलिए छोड़िए, no problem. Anybody else to answer any other application? No one. Very good, excellent. There are 44 sitting. No one is of use. चलो ठीक है. No. Muhammad Abrar, he is also trying to say answer, no problem, but listen all of you. Dalton's law is applicable only for non-reacting gases. बेटा uses अलग चीज है, uses का मतलब applicability नहीं है, right? Applicability अलग चीज है, uses अलग चीज है. बात समझ में आ रही है? साइंस में हर लफ्ज की ब्यूटी और उसका इंपॉर्टेंस समझना चाहिए. अप्लीकेबल कब होता है वो अलग चीज है, यूज कहाँ होता है वो अलग चीज है. ठीक है, चलिए. That is called applicability, right? Come on. Now comes to the last law. When we are discussing gas laws, we are having Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law, ideal gas equation. We have two more equations. One is called Dalton's law. We have done yesterday. Today we are trying to complete another one known as, what is it known as? Let us first of all try to understand the background of that discussion before declaring the name. Suppose, for example, you are having a container in which we have taken, say for example, a jar you have taken, and if you see carefully the figure, you can say, sir, this figure we have done in the last classes also. Yes. Suppose for example, you are saying that there is a gas here in this case, say for example, red colored gas I have taken here, and here I have taken another gas, another jar in which we have another colored gas, say for example. If it is so, then Suppose, for example, if you are allowing them to move, that means if you simply remove the lid, then what happens? Remember that the gas molecules which are having intermolecular force of attraction 0, number one, and number two, they are having random motion because of these two reasons, because of least almost zero intermolecular force of attraction, and because of what we can say random motion, these red colored gas molecules will try to move from this container to this container. This green colored molecules will try to move from this container to this container, and this movement is called intermixing. And this intermixing is not under the influence of pressure. It is possible by itself. You need not to have to apply pressure. There is no need to apply temperature. And suppose, for example, if you are doing so, then what we can say, sir, it is known as spontaneous intermixing. This is known as diffusion. Yes, I have defined this in the first class when we are discussing characteristic properties of gaseous state. So spontaneous intermixing of gas is known as diffusion. Now, when you are saying diffusion as intermixing, then there are two cases. One is, what is the reason for intermixing? What is the reason? You said, sir, intermolecular force of attraction is 0 and they are having random motion of gas molecule. This is the reason. This is the reason. Fine. Next, if suppose, for example, this is the reason, then what are the factors? Remember, reason is different, factors are different. Okay, applications are different, uses are different. When we discuss applicability is different. As here also, what is the reason of diffusion? Intermolecular force of attractions are 0 and motion of gas molecules. Okay, what are the factors which influences? Very simple, sir. The factor is only one factor, right? You are allowing two students of your classroom to run from a point to a target. One fellow is very fat boy and one fellow is very slim boy, and you are asking, come on, run from this point, and the target is given to you. Naturally, what you will conclude? You conclude, sir, the fat boy will take more amount of time to go to the target and the slim one will take less amount of time. Okay, this means to say rate of coverage of distance by the boy is inversely proportional to its heaviness. Exactly in a similar way, whenever gases are allowed to intermix, right, then the rate of intermixing, no sir, let us use scientific language, rate of diffusion. Yes, rate of diffusion is inversely proportional to what we are thinking, that sir, heavier gas should move slowly, lighter gas moves fastly. Heavier gas, how do you measure heavier gas? Density. Denser gas, lighter gas, less density, more density. Therefore we can say, suppose for example, if I am talking about this, then we say it is rate is directly proportional, inversely proportional to density. But there was a fellow by name Graham. He has taken mathematical and experimental calculations and he has declared, which we are discussing today under the heading of Graham's law of diffusion. According to this Graham's law, rate of diffusion of a gas is inversely proportional to square root of density at constant temperature and pressure. That means there is no need of application of higher pressure or higher temperature. If suppose, for example, you are talking about application in simple way, that sir, if we are discussing Graham's law, it is directly rate of diffusion is inversely proportional to square root of density. Heavier gases will have slow rate of diffusion, lighter gas will have fast rate of diffusion. Okay, nice. Once you understand this, then you can say, sir, density can also be related to some other parameters other than heaviness. Heaviness can be measured in terms of density. One of you stand up on the bench, sir, no. Density, heaviness can also be discussed in terms of molecular mass. I have to say, very good. Another boy says, sir, can I discuss in terms of vapor density? I say, yes. Therefore, rate of diffusion of gas is inversely proportional to square root of density. Very good. Inversely proportional to square root of molecular mass. Yes, you're right. Inversely proportional to square root of vapor density. Yes, rate of diffusion is dependent upon heaviness, and heaviness can be expressed in terms of any one of these properties, right? Suppose, for example, if you have taken mixture of gases, then rate of diffusion of gas 1, rate of diffusion of gas 2 is equal to under root, what I should say, d2 by d1, inversely proportional to square root of density, square root of molecular mass. And okay. Now, if suppose, for example, you are discussing this type of approach, then you can say, sir, if suppose I want to have comparison, then how do you proceed for comparison? Let us enjoy the game like this. Direct questions. Suppose, for example, they ask you something like this. What to do? Very simple, sir. I can do it with less usage of time. How can you proceed? Inversely proportional to molecular mass. And then apply root. Job is finished. 2 and 2. What will be the answer? Sir, answer is supposed to be given as root 2 is to 1. Suppose you are saying, no, no, sir, rate of diffusion of hydrogen, rate of diffusion of methane. What to do? Very simple, sir. 16 is to 2. Apply root. No, 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 no. Example is rate of diffusion of hydrogen to rate of diffusion of oxygen. No problem, sir. Rate of diffusion of helium, methane. Very simple, sir. Rate of diffusion of methane. Very simple, sir. Rate of diffusion of carbon monoxide, nitrogen. This is your job. Can you please help me? Yes. One is to one. Hakhan is saying 1:1. Very good. Muhammad Shoaib, 1:1. Nice. Excellent. Can you please help me? Zahiruddin is saying 1:1. Very good. Rate of diffusion of carbon dioxide to nitrous oxide. Go ahead. Go ahead. Muhammad Shoaib, he's saying 1:1. Is it correct or wrong? Anybody else? Yes, 1:1 because both of them are having same molecular mass. Very good. Come on. Now the question is, if you are discussing rate of diffusion, you can say, sir, first of all, let me try to enjoy mathematical meaning. Theoretical meaning, you understood how fast they are moving. Rate of diffusion. Sir, I want to enjoy mathematical expression. Rate of diffusion. Whenever we use the word rate, usually we talk with respect to time, rate of change of position, displacement, rate of change of velocity, acceleration, something like that. Rate of diffusion. What is rate of diffusion? Volume of gas diffused by time taken. right? How much amount of the gas has been diffused by time taken? Right. So someone says, sir, PV is equal to nRT. If suppose, for example, you are saying that PV is equal to nRT, if it is so, then temperature is constant here, pressure is constant here. So therefore, volume is directly proportional to number of moles. Therefore, shall I say like this, sir? Number of moles of gas diffused by time taken for diffusion. Yes, it is also called rate of diffusion. No, sir. Shall I say like this? Suppose, for example, here in the case of this case, the gas molecules are coming out. If suppose volume is more, diffused volume is more, diffused number of moles are more, they will cover more distance. Yes, area of cross section is constant. Yes, therefore, rate of diffusion can also be defined as distance covered by the gas, time taken. Therefore, if you want to enjoy this type of expressions, R1 by R2 is equal to under root M2 by M1. No, sir, this is equal to volume V1 by T1. No square root, nothing. Directly proportional to volume, inversely proportional to time. And then volume of gas diffused to time taken. No, sir. Number of moles of gas diffused by time taken. Number of moles of gas diffused by time taken. No, sir. Distance covered. Don't write D. Density. Distance. DIS. Distance covered by one gas. T1. And distance covered by another gas. T2. Hence, we can enjoy different type of mathematical problems to face out how much is the diffusion with respect to density, molecular mass, volume of gas diffused in time taken. Go ahead. Write the statement of transfer. Here there is a space.
एक मिनट कर दे क्या तो
अपना कोई कार्गो नहीं है अभी
कार्गो क्या कि वो कहीं अटक गया करते बीच में कॉलेज बोले ना मावा बीच में शिप में वेव्स कुछ आया था पलट गया वो हमने बोल रहे हैं
शिप पलट गई
शिप को रोक दिया हार्डवेयर बेटा वेव्स आने की वजह से तो और 10-15 दिन कुछ लगते हैं बोल के वो अंदर ढक लो आप खाली उठा कर ढका दिया ना कर दिए तो ये बैग भी ढक लो आराम से
ना करो उसको आइज रखो ना यहाँ की कुछ
इधर मेरे का सामने ये बंद करके नीचे निकाल जिम लगा बैठे हैं तो बैग आज भी नहीं लेके आए उधर क्लास है भी आपकी जरा उधर उधर अली
बोलिए अम्मी
क्लास है भी आपकी
क्या था फिर आप
देखो ने वाला क्लास है सब कुछ नहीं
वो ये पकड़ के रख रहे उन्हें निकल के आया था कितना पुराना लैपटॉप है वहां है
बहुत पुराना नहीं है इससे पुराना लैपटॉप है बाबा का तुम्हारा इससे पुराना यूज कर रहे हैं ना बाबा
हां तो ऐसा पकड़ रहे थोड़ी थे अब
उधर ढक लो अंदर पकड़ लेकर अंदर रखो
दीप लगाओ यार बोले क्या बोली
यार यहाँ लॉक हो गए
छोटी नहीं मतलब देखिए यहाँ पर खुद जा रही दिख रही अरे ऐसी रखा है इसके नीचे
रखना है
उठा और बोलता है
चलो तब तक जरा ये कर मेरा थोड़ा परेशान मेरे भाई मेरे काम में
थोड़ा और हाँ अरे क्या और
खाऊं हो गया भाई
Is it over? Go ahead, go ahead, go ahead. Shall I proceed? Abrar, is it over? Fine. Now, if you want to understand the other way of enjoying Gram's law of diffusion for solving numerical problems, we can also done like apply the concept like this. Suppose, for example, you are discussing something like this. There is a long tube. Say, for example, 100 centimeter length. From this end, I am allowing ammonia gas to go inside. Okay. From this end, I am allowing HCl gas to go. Okay. Now, before learning this, I'll tell you one more beautiful statement. Let us take this one. Suppose, for example, you are having a container in which you have taken gas, alone gas, right? Now, if suppose you are having this type of situation and then there is a small puncture made here, then what happens? The gas molecules will leak out. Something like this, right? Now, once you are having leaking out in this is called as effusion process. In the previous classes, when I have given you characteristics of gaseous state, I said leaking out, escaping out of a gas through a small aperture is known as effusion. This is called as effusion process. Remember, Gram's law of diffusion is also applicable for effusion process. Naturally, from this hole, if the gas is denser, it will come out faster. If the gas is lighter, if the gas is denser, it will come out slowly. If the gas is lighter, it will come out fastly. And if you're having mixture of gases, here if it is so, I can directly apply rate of diffusion is inversely proportional to square root of density. It is inversely proportional to square root of molecular mass. This is okay, fine. But suppose, for example, if you are having, no, sir, I am having mixture of gases. If it is so, then if you make a puncture, suppose, for example, you are making a small hole here, then what happens? Through this hole, both of the gases will come out. Right? Now, if suppose you want to apply rate of diffusion of gas 1 and gas 2, then there are two cases possible. Case number 1. Suppose, for example, if N1 is equal to N2. What is the meaning of this? Number of moles of gas 1 and gas 2, 50 moles of gas A and 50 moles of gas B I have taken. In that case, only factor is density and molecular mass. Suppose, for example, if you take this one, then R1 by R2, as usual, what we are saying previously, density 2 by density 1, or it is N2 by N1. No, sir. Suppose the case is something like this. I have taken mixture of gases. And in that case, if I am allowing the gas to escape out from the pinhole, suppose, for example, if number of moles are not equal, okay, then what happens? Nothing will happen, sir. First of all, you have to say who is denser, who is lighter. Afterwards, there is one more statement which is important. Suppose, for example, if N1 is more than N2, what happens? N1 is more means moles are more. If number of moles are more, collisions on the walls of the container is more. If collision is more, force is more. If force is more, escaping out tendency is more, right? This means to say, if N1 is not equal to N2, here N1 is equal to N2 can also be given as P1 is equal to P2. Because in this vessel, volume is constant, temperature is constant, PV is equal to nRT. If number of moles are equal, pressure must be equal. If number of moles are not equal, pressure is not equal. Which pressure? Internal pressure. Yes. pressure of the gas. And if suppose you're having this one, then we can say, sir, R1 by R2 is equal to, okay, let me enjoy first one and then we'll go for second. Rate of diffusion is inversely proportional to square root of density. Very good. No, sir. Apart from this, it also depends upon internal pressure. It also depends upon internal number of moles, right? These are n number of moles in the vessel. In the vessel, if more number of moles, more amount of diffusion, directly proportional. Therefore, modified form of Gram's law of diffusion can also be given as rate of diffusion is directly proportional to pressure, not outside pressure, inside the pressure, inside the pressure, and different root of density. Okay. Now, those who are sincerely enjoying the game of Gram's law of diffusion, sir, you are missing one statement. What is that? You are saying pressure. You should say difference in pressure. Difference in pressure. Listen carefully. Listen carefully. Those who want to become advanced rankers, listen carefully. Sir, you are saying rate of diffusion is directly proportional to pressure of the gas inside the vessel. I think something is missing, sir, in your statement. What is that? The rate of diffusion is directly proportional to difference of pressure inside and outside. Suppose inside pressure is very much high, outside pressure is very much low, fast diffusion takes place. Now I'll keep inside pressure 20 atmosphere, outside pressure 1, 2, 3, 5, 10. What happens? As I'm increasing the outside pressure, rate of diffusion decreases. Okay, okay. This means to say, sir, you have to count both the pressures. Yes, you are right. Remember that I should account both the force pressures, that is difference in pressure. But conceptually, we are going in the right track. But outside pressure is always a constant quantity. Atmosphere is supposed to have always constant quantity. Therefore, it is not counted. Basically, I should say that rate of diffusion depends upon difference in pressure of in and out. Are you able to understand? But outside pressure is supposed to be almost constant 1 atmosphere. Therefore, we do not write that one. Okay. Conceptually, we should be very strong. Hence, R1 by R2 is equal to P1 by P2, modified form of Gram's law of diffusion. No, sir. N1 by N2. What is N1, N2? N1 is the number of moles inside the vessel. N2 number of moles inside the vessel. Under root D2 by D1. Right? Better enjoy the case of not density, because most common language is molecular mass. Both are same. We can write like that also. This is better enjoyment. N1 and this is and this is okay. Once you understand this, come back here. We are allowing ammonia, molecular weight 17. He will say, I will run very fast. Molecular weight HCl. He will say, I am a very fat boy. I will run slowly. Okay. Now, when they are running here, naturally, ammonia will cover more amount of distance. HCl will cover less amount of distance. Therefore, the question comes, where is the meeting point? Sir, they are meeting somewhere here, which is towards HCl. Are you able to enjoy? Thus, they are meeting at point P. And this meeting point P will be away from ammonia and close to HCl, right? And suppose, for example, he will ask you, what happens here? At this meeting point, there is a formation of a substance known as ammonium chloride. Ammonium chloride appears to be as white dense fumes. And therefore, examiner will ask you, where do you have formation of white dense fumes? From ammonia and from HClM. He will ask any style. Conceptually, we should say, let us assume this is at a distance of x from ammonia. No problem. This is 100 minus x. Right? Once we have this one, then apply Gram's law of diffusion. R1 by R. No, 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 no. R of ammonia by R of HCl is equal to under root 36.5 by 17 is equal to without root distance covered by ammonia, distance covered. What is this? No, distance covered by ammonia, time taken by ammonia, distance covered by HCl, time taken for HCl. Right, this is root of 36.5 by 17. You people are genius in mathematics. You can simplify that distance covered by ammonia, distance covered by HCl, time taken for both of them will be definitely same, right? Like this we can find out where do we have formation of white dense fumes, right? On the basis of this, different questions have been created. One author or one textbook person said, okay, okay, let us enjoy a game. Suppose, for example, you are having a classroom, walls are straight, something like this. If suppose, for example, this classroom has two doors, one entry, say for example here, and one is exit, say for example here, something like this. This is filled with certain rows of benches. One, two, three, four, five, dash, dash. So many are there. Similarly, here also we have boys and girls enjoying the position. Fine. Suppose, for example, one office boy came inside from here and he has a jar containing laughing gas, nitrous oxide. And another office boy is allowed to come from here and he has a tear gas in jar. And when they came inside, simultaneously at the same time they have opened the jar, right? The examiner says this consists of 20 rows in the class, at which row the students will start crying and laughing simultaneously. Find the number of row where the students will have both the process of crying and laughing. For that purpose, apply same type of approach and you can calculate the answer, right? Come on, don't cry. Enjoy the game and write down the whole as it is. Go ahead. कौन है? इधर आओ बाहर, बाहर, इधर आइए। ऊपर के वास्ते बोला था हमने 10 दिसंबर को बोला। दिसंबर 10 तक का है। पापा क्या बोले 2 जुम्मा के बाद बात करेंगे। हो जाए जी हाँ। तो कहते थे वो तो बिल्कुल जवाब देते हैं। ठीक है मैम। Abdul Wajid, why you were disconnected again? After so many days, you have a complaint disconnection. You are using mobile data or you are using Wi-Fi? Abdul Wajid, नो आंसर। चलिए ठीक, कोई बात नहीं, डिस्कनेक्ट। There is power cut problem. Very good. Nice. In the last point, what I said, that there is a classroom. Say, for example, your classroom. All of you are sitting, 49 students were sitting in the classroom. And then there is a door one side of the classroom where a boy came by taking laughing gas jar. And from the other side, another boy came with the. Let him go, let him go. Okay. If the other side, the other end is coming with tear gas and both of them are opened simultaneously, naturally nitric gas, like tear gas, will have different molecular mass, laughing gas has different molecular mass. Therefore, there will be different rate of diffusion. So when they meet together at that particular row, if you are sitting Wajid, then what you will do? You will cry and laugh simultaneously. Ask you, what is the problem, right? Is it disconnection problem? You say, no, sir. The problem is laughing gas is coming from one end, tear gas is coming from other end. Therefore, I am enjoying the situation known as simultaneous laughing and crying. Examiner will ask you, Abdul Wajid, tell me on which row you are sitting. Number of rows are 20 in the classroom. Find the number of row at which students will cry and laugh simultaneously. Hope I have given the answer properly. Is it clear? Done. Very good. Is it over? Is it over? Okay, nice. Now that is the end of Gram's law of diffusion, right? As we have said in the previous class, uses of Gram's law of diffusion. Similarly, here Dalton's law. Here also we have to write uses of Gram's law of diffusion. Please, at least now, in case of Dalton's law of partial pressure, only two students were there to respond. Now, evening or try to sit at home and see what are the uses and write down all the uses, right? And tomorrow we'll discuss numerical problems based upon Gram's law of diffusion. Mohammed Shoaib. Shoaib is saying x is equal to 59.3. No problem. Problems we are discussing, numerical problems we are discussing tomorrow. I'll add up your answer in the next class. Thank you. Assalamu alaikum.